Hi. Hi, thanks Mohit for this nice introduction. Thanks everyone for joining remotely, and special thanks to Kalpesh for organizing this meeting. I should say this is my first time giving a talk remotely like this, so I hope this runs smoothly. And feel free to ask questions. You can use the raise your hands feature, and people who moderate this or use the chat or unmute yourself. So this talk is our attempt to bring a new methodology into the interpretability world in neural NLP, where we try to adopt ideas from mediation analysis, a method introduced by Pearl and others in the causal inference literature. And we borrow those ideas and try to adapt them to the case of deep language models. And there's a test case of applying this to detecting and analyzing gender bias. This is joint work with a number of people at Harvard and other places. The lead authors are Jesse, Vic, Sebastian German, and myself, with contributions from Sharon, Daniel, Yaron, and Stuart. Okay, so here is a deep neural network, also known as a black box, and it maps some input to output. And there are various questions we might want to ask about this neural network. You might wonder how good it is, and we have various benchmark data sets and leaderboards to measure performance of various models on various tasks to tell us. Sometimes we are more curious at how to understanding how it behaves. So, for example, people construct so-called challenge sets or test suites. The idea behind those is that instead of giving an average performance of some model on some task, we try to break down the performance to very many different examples that are trying to capture various kinds of properties or linguistic phenomena. So we might have a challenge set that detects the ability of this neural network to perform various kinds of semantic understanding tasks, or a very fine-grained, nuanced morphological properties, and so on. This has been going on for a while in the computational linguistics community, but it's also becoming more and more popular recently. So that's more about how this network behaves. On the other hand, we're maybe curious to figure out what's going on inside it. What are the internal representation in these models? What kind of information they capture? And one of the prominent methodologies to go about that is to use a classifier, sometimes known as a probing classifier or an auxiliary classifier, where the idea is that we take a model that was trained on some task, maybe it's a machine translation model or a language modeling network, and we collect representations. So run this model on some data, collect representations from various layers, for instance, and then try to decode what's inside those representations by training another classifier. And that other classifier is trained on some linguistic annotation task, which we are curious about. So for instance, we could ask what kind of part of speech information is captured by these models by building a part of speech tagger that takes internal representations from a deep network and predicts parts of speech. And if that performs well, we may consider the representations to contain a lot of information about part of speech. So that could be seen as a way to look inside the model, look at the structure of the model more than the way it behaves. But then there's another question, which is, how does this model work? What are the internal mechanisms or internal computations that cause it to generate a prediction or behave in a particular way? So not just looking at its behavior without looking inside, but like to understand what's going on inside that influences the behavior in a particular way. And that's the focus of our work here. So there are all sorts of taxonomies or categorizations of interpretation methods that I like to briefly go through. One common distinction is between post hoc analyses and intrinsic interpretability or transparent models. So a post hoc analysis is something that takes a network or a model that was trained and then tries to understand what's going on with this model, tries to figure out something about it. An intrinsic method or a transparent model is some way to change the model or make the model intrinsically more transparent or intrinsically more interpretable. For instance, you might think of a decision tree algorithm as something that's intrinsically more interpretable than a deep neural network. Some people draw distinctions between global interpretations and local interpretations. A global interpretation looks at the model as a whole and tries to tell us something about that model. For instance, the probing classifiers approach is a global interpretation method. A local interpretation or local analysis is trying to explain one particular decision of this model on one instance. So for example, if you're familiar with saliency maps, feature attribution methods, and things like that, these are local interpretation methods in that they say something, they explain one particular decision of the model. There's also a distinction between structural and behavioral analyses. A structural analysis tells you something about the structure of the model. Again, the probing classifiers are an example of a structural analysis. A behavioral analysis tells you something about how the model behaves, but not anything about its structure. So a carefully constructed test suite or challenge set can be seen as a behavioral kind of analysis. And finally, some people draw distinctions between model level understanding and decision level understanding. This is a little similar to the global versus local distinction. The point being whether you say something about the model as a whole or one particular decision of that model. So here's a little table that I gathered from work by Sebastian German and Hendrik Strobel, classifying a bunch of different or categorizing a bunch of different analyses techniques. So in particular, our goal here in this work is to provide a method that is both global and local at the same time, both structural and behavioral at the same time. It tells you both something about the model and about its decision at the same time. Okay. So I'm going to stop here for a moment before I go to the actual examples and see if there are any questions. Okay, no questions. So let's see an example. Our particular interest in this work is gender bias. So imagine that you have a prompt or a prefix such as the following: the nurse said that, and you get a language model and you ask the language model to complete this sentence, to fill in the blank or to continue this sentence. So here's an example that I got when I used this nice tool, Write with Transformer. This is using GPT-2, which is a large-scale transformer-based language model that was trained on a bunch of data, and it produced this this sentence. So I fed in the nurse said that, and I got the nurse said that she had been told by the hospital that she was not allowed to leave, and so on. Now compare this to the next example. When I feed in the doctor said that, I get this continuation. He had been told that the patient was suffering from a rare form, and so on. In particular, you may notice that the sentence, the prompt with the nurse is continued with the word she, and the prompt with the doctor is continued with the word he. So this is obviously an issue reflecting some kind of gender bias, associating nurses, the nurse profession with women and the doctor profession with men. And there's a lot of work on identifying this kind of gender bias in various language representations, starting from word embeddings, static word embeddings, and like word2vec or glove, and all the way through more recent contextualized word representations like Elmo, BERT, GPT-2, and these kind of things. And it's quite clear where this is ultimately coming from. So these models are trained on a lot of texts that were created by people, and these texts reflect some kind of biases that happen in our society. So presumably in the underlying training data, the word nurse was more commonly associated with women, and the word doctor was more commonly associated with men, leading to that kind of bias in the model. But our question is a little different. Our question is what in the model causes it to generate a bias prediction? So we understand this is happening ultimately because of the training data, but there must be some kind of internal mechanism that's happening in the model that is making it generate these biased predictions. And that's what we are trying to figure out in this work. Okay, so I have here a slide to stop for questions. So I'm going to do that for a few seconds.
Yeah, feel free to use a chat or the hand raising feature if you have any questions.
Okay.
Yeah.
Good. No questions, then I'll continue. So our take on this question is to use ideas from causal mediation analysis. And this is a framework introduced by Judah Pearl, which aims to study how information flows from input to output in a model, and identify which components mediate this information. So here is some broad diagram showing that. We have in this framework a control variable X and a response variable Y, and potentially we might have an intermediate variable Z, also known as a mediator. And the idea of mediation, causal mediation analysis, is to measure what's the effect of X on Y, and in particular, the most appealing idea is to distinguish two kinds of effects: the direct effect of X on Y and the indirect effect of X on Y. So the direct effect of X on Y is what flows directly from X to Y. This is the solid line in this diagram. The indirect effect is whatever flows through some mediator, in this case Z. So these are the dashed lines. And you can maybe start imagining how this kind of approach can help us when we try to figure out how information flows from input to output in a deep model, and what are the mechanisms. Are there particular mediators or intermediate variables that mediate such information more than others? So I'll define these more formally in a moment. Okay, so let's go to some definition. We'll assume that we have a language model which predicts the next word, probability of xt given all the previous words. And we'll use examples such as the ones that I've shown before. So imagine that you have a prompt, the nurse said that, and there are two possible candidates to continue this prompt. There's the stereotypical candidate, she, and the anti-stereotypical candidate, he. So we'll define a particular measure of bias. So this, our Y, will be a bias measure, which is the probability of the anti-stereotypical candidate over the probability of the stereotypical candidate. Or in our case, in this example, this will be the probability of he given the nurse said that, divided by the probability of she given the nurse said that. So if intuitively, if y is smaller than 1, the prediction is stereotypical. If y is larger than 1, then the prediction is anti-stereotypical. So that's the first thing we have. The next is we have to define interventions. So in mediation analysis, we make use of interventions, also known as do operations. These are operations that you apply on your input. In our case, we'll have 2 such operations for every example sentence. One of them will be set gender. So in this case, we replace an ambiguous profession such as nurse with an anti-stereotypical gender-specific word. In our case, we use man. So this is anti-stereotypical, and it's specific. It has a specific gender. And we'll also have a null operation, which doesn't do anything, just leave the sentence as is. Here are some examples to understand how this works. So if we apply set gender to the nurse said that, we get the man said that. If we apply set gender to the doctor said that, we get the woman said that. And if we apply null to the nurse said that, then nothing happens. We stay with the nurse said that.
Yonatan, we have a question. Subhendu?
Yeah, I just had a quick question. So we would choose, how do we choose the stereotypical and anti-stereotypical candidates? So it looks like that has to be based on general knowledge. And how often do these actually correspond with what the model says? So are there any examples of the model picking anti-stereotypical candidates? So is there any cases where y greater than y is less than 1?
Yeah, good question. So we choose the stereotypical and anti-stereotypical candidates always to be, always to be man and woman in this case. So they are kind of the prototypical examples of a gender specific, like a female specific word or a male specific word. But there's another aspect which I think you are touching upon, which is how do we know that nurse is stereotypically female and doctor is stereotypically man? And for that, we actually utilize external statistics that come from the Department of Labor statistics associating certain professions with certain gender words. You also asked about the bias measure, whether it can be smaller than 1. Yes, so we looked at the correlations between those external statistics of stereotypicality and the model predictions, and there is indeed a correlation. It's not perfect though, so it's not always consistent, but there is a fairly reasonable correlation in this data set that we've used. Any other questions? Cool. So given these operations of set gender or null, we define another value of y, which is y sub x of the example. This is the value that y obtains in a particular example under the intervention. For instance, y set gender of the nurse said that works in the following way. We first apply the set gender operation. So we change the nurse said that to the man said that. And then we calculate the y value as the probability ratio as before. So we have the probability of he given the man said that over she, the probability of she given the man said that. Okay, so after we have defined our interventions, we are ready to define the different kinds of effects. And the first value is known as the total effect. This is the difference between the amount of bias under a gendered reading, like the man said that, and under an ambiguous reading, like the nurse said that. And I'll show the equations in a moment, but intuitively what this means is we first have the example, the nurse said that, we run it through the model in a forward step. This is shown in blue in this diagram. And we calculate this probability ratio, and we get a value y. Then we apply the operation, the set gender operation. We get the example, the man said that. We run that through the model, again, in a forward step, get those probabilities, calculate the probability ratio. And then what we take is the difference. So here are the equations. The math is not so important. What this does is it takes the y set gender and subtracts the y null. So it's the difference between the two. And there's you may notice there's a normalization here where we divide by y null. This can be done for one example. That's what I'm showing in the first line of equations, or we could average this over a data set of examples, such as the nurse said that, the doctor said that, or other examples, and then we obtain a corpus level or an average total effect. And this, by the way, is already hinting how this approach can move from a decision level analysis to a model level analysis. Okay, so this was the total effect. What we are more interested in are so-called direct and indirect effects, which I've mentioned before. Here, the idea is to define a mediator z, and z is an intermediate variable between x and y. So in our context of deep neural networks for language modeling, you can think of z as one particular neuron in the model, or maybe it's a full layer in the model, or one attention head, or one attention weight, and so on and so forth. Anything that can be decided or observed inside the model. So we'll have our control variable, which is the operations applying set gender or null. We have the response variable, that's the bias measure, and various kinds of mediators. So now let's define direct and indirect effects. The indirect effect is the change in bias when keeping the example as is, but setting z, the mediator, to the value it would attain under a genderized reading. So this is kind of a counterfactual setting where we compare two quantities. On the left, it's the same quantity that we've seen before. We take the example, the nurse said that, feed it in, measure the bias measure y. On the right, what we have is a kind of counterfactual. So we imagine what would be the value of z if we were to feed in an example of the man said that. And in practice, to implement this, what we do is we actually simulate, we run the model with the man said that in a forward step. We record all those values of the different mediators. Then we go back, we plug in this red circle here that you see, changing one particular neuron in this case, and again, run the model in forward step and calculate the bias measure. Here are the equations. So this is an indirect effect because what it does, it holds fixed one particular neuron, and what it measures is the effect of flowing through that particular mediator or that particular neuron. Hence, this is an indirect effect. Kind of analogously, we have a direct effect. This is the change in bias when we genderize the example u, so we apply the set gender operation, but we hold the mediator z to the value it had before under the ambiguous reading. So again, on the left side of this diagram, we show the base case where we just feeding the nurse said that, calculate the bias measure. On the right-hand side, we show the intervention. So here we apply the set gender operation. We get the man said that. We feed this example for the model, but we hold one particular mediator, in this case, one neuron, to the value it had before under the unambiguous reading. That's the one in blue. And again, we compare the difference between the two to calculate the direct effect. Okay. So these were the direct and indirect effects. I show this as an example of a mediator, which is one neuron. So mediators can be various things. In our experiments, we mostly focused on two kinds. One was neurons. So Z can be one neuron, or it can be a group of neurons in the hidden representations of the model at each layer. So to do that, to study that, we used a data set of templates, such as the occupation said that, the occupation yelled at, whispered that, wanted that, and so on. They are listed here. And we instantiate those templates with a list of professions coming from prior work. And after we have those all those examples, the particular mediator that we study is the neurons at the representation corresponding to the profession word. So we'll feed in an example like the nurse said that, run it through the model. We have a lot of layers, but what we look at is the representations corresponding to the word nurse in any one of the layers, and in particular, one or more neurons from those hidden representations. That's for neurons. The other aspect of these models, which is very prominent in transformer-based models, is attention. So we looked at setting mediators Z to be an attention head, or maybe a group of attention heads. And I'll remind what those mean in a moment, if you're not familiar with them. So to study attention, we used a collection of two data sets from prior work known as window bias and window gender. Here's an example from window bias. It works a bit differently from what I've shown you before. So in window bias, you have a prompt, and the prompt may be something like, the nurse examined the farmer for injuries because she, and then there are two possible candidates, either was caring or was screaming. So the stereotypical candidate is was caring. That's based on a bias associating she with the nurse, making the continuation was caring more likely. And the anti-stereotypical candidate was screaming, because if she is associated with farmer, that would be an anti-stereotypical reading, and that would make was screaming more likely. So window bias and window gender come with these sorts of examples, not exactly in this format, but we repurpose them for our purposes. This is just a reminder. If you're not familiar with with attention, the idea behind attention is to represent a collection of words or a sequence of words by taking a weighted average of all the words. So here I'm showing an example of how this is done. We would like to get a representation for the second word. And we are trying to calculate the representation y, y2. That may be in some upper layer. This is based on all the previous representations from a lower layer, those x's, x1, x2, x3, x4. And in red, you see weights. These are weights that are used to get a weighted average of those representations. And they are obtained by various calculations that are not so important for our purposes. The point here being that the representation of y2 depends on all the representations of the other words from the previous layer according to these weights w. And when I speak of attention heads in this work, what I mean is the set of weights w. So if we set the mediator Z to be one attention head, that means we take the set of attention weights W and change it to be something else. In practice, there are multiple kinds of sets obtained by multiple attention heads, so we may speak of more than one in this model. Okay, this is just a recap. Okay, so going back to our mediators, Z. So we have these examples, like the nurse examined the farmer for injuries because she either was caring or was screaming. And we defined the bias measure. So as before, the bias measure Y is the probability of the anti-stereotypical candidate divided by the probability of the stereotypical candidate. So in this case, Y will be the probability of was screaming given U divided by the probability of was caring given U. And we'll have another kind of operation. In this case, we define a swap gender operation. So this changes she to he. That's a little different from the operation we had before, which was a set gender operation. But then the total effect is defined in the same way as before. It is the difference between Y swap gender of U and Y null of U, again, normalized. And once we have those definitions, then the direct and indirect effects are defined in the analogous way. Namely, we apply those interventions on a mediator and again calculate these differences to get the effects. Okay, I'm almost ready for the experiments section, but before that, I'll stop again to ask for questions.
Yonatan, I had a quick clarification question. So is it necessary that the Z has to be, so is it necessary that there has to be a path between X and Y? The Z should not block all the paths from X to Y, right? Right,
okay, good question. So if you can have the Z block all the paths between X and Y, that's fine. I mean, there's nothing stopping you from doing that. It just makes the analysis not so interesting or kind of trivial. So
right.
if Z blocks the entire path between X and Y, then we are back to the total effect case. There's nothing special about, or the indirect and direct effect kind of, the indirect effect becomes zero and the direct effect becomes exactly the total effect in this case.
I see. So I was wondering whether you can measure things like how important a particular layer of the neural network is, because I guess a layer will completely block the path. Like if you take the entire layer as Z.
Yeah, that's a very good observation. So, and we've seen that. So if you set the entire layer representations, so the hidden states, if you set them as the mediator, then whatever comes after that, you can't say much about that. But what you can do, I mean, you could still measure to see the importance of different layers. It's just that it kind of becomes less interesting to say something about all the previous layers, because all the previous layers are not so important if you just fix one particular layer. But things might still happen later on. The other aspect is to look at the attention. When you, even if you set the entire attention, all the attention heads in a particular layer to something, you still have information flowing through the representation. So that doesn't cover everything.
Okay, we have a question from Subhendu.
Yeah, I had a question on the similar lines. So you were talking about choosing an attention head, like choosing one of the attention heads through which your control variable travels, right?
Yep.
So in most of these transformer models, you have multiple layers, and and the word travels through the multiple layers. So when you choose an attention head, do you choose all the other heads that attention head interacts with over all the layers, or are you talking about one attention head and one layer for that particular word? What exactly are you changing the outputs of?
Yeah. So if I speak of one particular attention head, then we are changing only that particular attention head in one particular layer. But we can also talk of multiple attention heads, and I'll show some results about that, either in the same layer or more broadly in any layer.
Okay, I think we can proceed. No more questions. No more raised hands. Yeah.
Okay, so let's look at some of the experiments that we had. So for the experiments, we focused on the GPT-2 model as a large pre-trained language model. This is a transformer-based language model trained on a bunch of data. Fortunately, there are several different model sizes that are available in the Hugging Face library, and these are the ones we use, from small, medium, large, extra large. There's also a distilled model that we've looked at. And here are some of the results. So we have here a list, a table of showing the total effect. So there's no mediation yet in this case. We are just changing the example, not doing anything inside the model yet, just changing the input and see what happens to those probability ratios. And I'm showing here a bunch of different models and 3 different data sets. We-know bias and we-know gender are data sets that we use to study attention. And the professions data set is the data set we use to study the role of neurons. So the professions data set is those examples like the nurse said that, the teacher said that, the teacher whispered that, and so on. And we-know bias and we-know gender are these examples where you have 2 possible antecedents like the nurse and the farmer, and you need to figure out the continuation. So a couple of things, interesting things to see here. The first row shows a random model. So this is just taking GPT-2 and setting all its parameters to be random. The point here is just to show a sanity check that trained models have larger effects than the random models. The random model effects are actually much larger, much smaller, sorry, than the trained models. More interestingly, as you go down that list of models, you increase the model size and you also increase the gender bias effects, the total effects. Now, it's not always consistent, but there does seem to be some correlation. We see it pretty well in we-know bias and we-know gender. When at some point, things kind of plateau. We don't exactly see it in the professions data set. There's a lot more variation in data set, but we do see that the extra large model has a much larger total effect than the other models. Okay, the other thing I should comment about is that the numbers, the magnitude of the numbers in we-know bias and we-know gender is very different from the magnitude of numbers in the professions data set. So the 2 are not comparable. They are very different data sets, and we study kind of somewhat different things. In particular, it looks like the effects are much larger in the professions data set. That may be understandable because these are examples where gender bias is very pronounced, like the nurse said that, the doctor said that, the teacher said that, and so on. Whereas in we-know bias and we-know gender, there are some somewhat more subtle cases where figuring out the bias is maybe trickier. So that's our explanation for why the magnitudes are much different. Okay, so that was just the total effects. We are more interested in the mediation. In particular, we asked a couple of different questions. And the first one is about sparsity. And it kind of starts going at one of the previous questions. So where in the model are the gender bias effects captured? Are they mediated by just a few components or a few mediators, or distributed all over the model? So to answer this, what we do is we measure the indirect effects flowing through different mediators Z. So each time we'll set the Z to be something different, say one head, run the calculation, measure the indirect effect, move to a different head, again, do the calculation and measure the indirect effect, and so on. So let's see what we get. This is an example of the indirect effect when we look at different attention heads. So in the heat map, the darker, when the color becomes darker blue, that means that there's a higher indirect effect. And the x-axis here is the head index, and the y-axis is the layer index. So the main point to take from here is that there are very few heads that have a large indirect effect in this case. And most of the heads seem to not contribute much to the gender bias effects in our case. Now this is for GPT-2 small. the heat map is showing what happens when a mediator is just one head. You can kind of see that it's just a few heads that are important, and they are around the same layers, around the middle layers of layer 4, 5, 6 or so. The bar chart on the right shows what happens when you set the mediator to be a full layer, in the sense that it's all the heads in the layer. So in this particular case, 12 heads. And again, on the calculation, this is showing that those layers of layer 5 and layer 4 are the most significant layers for gender bias. So this is for GPT-2 small. We've seen this pattern of sparsity in all the models that we've looked at. I'm not going to go through all of them, but you can kind of take a glance and see there are always relatively few number of heads that have large indirect effects, and moreover, they are concentrated in around the middle layers of each of the models that we've looked at. So this is for attention heads. Oh yeah, I also have a baseline. This is the random model baseline. So this is again taking a model that's untrained or set to random, measuring. You can see that there's not much to be going on at all. Even the bright colors that you see at the first layer are not significant. So the scale here is actually much, much smaller than what we've seen before. So basically there is nothing really going on in the random model. Okay, so the next question is how heads work together. I've shown what happens when you set just one head. Here I'm showing the indirect effects when we set Z to be an increasing number of heads. So we start with just one head, then we add another, and another head, and another head, and so on. And the point here being is that very quickly we hit this dashed line. This dashed line is the full effect of the entire model. That's what happens when we set all the heads at the same time to be the mediator. The point here is that you only need very few heads to reach that, that dashed line. And those heads that are the ones contributing the most are actually from those intermediate layers, 5, 4, and so on.
So we have a question, Nadir. Yeah.
Yes. So here you're able to have many different combinations of heads. Did you try to do a full set of the combinations of heads to see if it mattered which ones that you made available, or is this just one sort of structured approach of unmasking or including one additional head without looking at various combinations?
Yeah, great question. So unfortunately, it's intractable to do this exhaustively for all the subsets of heads. Even in the small model, there are 144 heads.
Okay.
So imagine, 2 to the 144, we can't do that. But what we did is we tried 2 different algorithms for selecting that subset. The greedy algorithm first select the one head that will have the highest indirect effect. So that it does that by trying all the different heads independently, selecting the one best. Then it sets that, and next it will try to add one other head, try all the other heads except for the first one, and find which one will lead to the greatest indirect effect, and add that, and so on. So that's also quite intensive. It's squared in the number of heads that we have, but we were able to run that. It took some time. So that's the greedy, that's shown in blue. The top K is even a more naive approach. That's just, what that does is we first try every head independently and rank them by the indirect effect, the independent indirect effect. And then we just add them incrementally by that ranked list, starting from the one that has the most indirect effect. But that's a fairly reasonable approximation to the greedy, as we see here. it's possible that there is a better subset of heads that we don't see here because of these approximated methods for subset selection. Okay. Yeah, so I'll continue. The point here being is that there are very few heads that are sufficient to satisfy the full effect of all the heads together. This was about heads. Here's a plot showing sparsity in neurons. So what I'm showing here is the indirect effect in each of the models that we tried, but only of the top 5% of neurons. So this is a very small number. The point here is that, and this is kind of different from the attention. So on the x-axis, we have the layer index. Each time we select neurons just from a different layer. And on the y-axis, we have the indirect effect of the top neurons in that layer. And what we see here is that the first 1 or 2 layers are the ones that have the largest indirect effect, which is different from the case of attention, where we saw most of the effect concentrated in the middle layers. And one could imagine that this has to do with the nature of the data. If you recall, for studying the role of attention, we use this profession data set example, like the nurse said that. So intuitively, the bias is perhaps concentrated in the word embeddings themselves, so closer to the input, which is maybe why we see this high effect in the first 1 or 2 layers. There's also a second jump, which you can see somewhere around the middle layers in each of these models, and that may be similar to the case that we've seen with the attention. Okay, and similarly, like before, we can run these algorithms for selecting groups of neurons. Here again, the dashed line is what happens when you set all the neurons in the model to be the mediator. And those colored lines are the top K. There's also the top K algorithm that I've described before. Either we run it on all the layers or just run it on the first few layers. Very quickly, we hit the full model effect. So the x-axis here is the log of the number of neurons, which means that actually this is happening very, very quickly. Okay. So the next question, after we establish the sparsity, is how the different components interact. It's true that we see very sparse components, so not many of them participate, but do they work together? Do they work independently? Are the effects amplified by different components when they work together, or constrained? Are they capturing different aspects? So part of the motivation for that is that we know that if you think of heads in transformer models, they do very different things. So there's a number of papers that have shown that heads in transformer models capture all sorts of aspects of language. So it might be interesting to see how they work together in our case. And does it show up in our methodology? Here's one study of that. Here I'm showing, again, the indirect effects of attention heads in various models. So the x-axis is showing various models. The y-axis is showing indirect effects, but they are calculated in two different ways. There's an NIE all and NIE sum. The NIE sum is the number that you get when you each time intervene on only one head, and then sum all of the effects that you got from those independent interventions. The NIE all is what happens when you intervene on all of the heads at the same time. So in the NIE all, the mediator is just all of the heads in the model. In the NIE sum, we have each mediator is just one head in the model, but we calculate the indirect effects and we sum them all up. The point here to note is that NIE all is roughly equal to NIE sum. So what you get from intervening on all of them at the same time is about the same thing as you get when you intervene independently and then sum up the effects. which we interpret as meaning that the heads are mostly independent and complementary, perhaps capturing different aspects of gender bias. And this is true for a variety of models that we've played with. Here's a qualitative example illustrating that. So here we are showing the sentence that I've mentioned before: the nurse examined the farmer for injuries because, and then we have two possible trigger words, either she or he. So on the left is the nurse examined the farmer for injuries because she. On the right, the trigger word is he. And the colors that you see are the amount of attention directed by those trigger words to all the other words. And each color is a different head. We show here the three heads that had the highest effects in this model. So let's focus on the left side for a moment. The nurse examined the farmer for injuries because she. So you'll notice here that there's a very large orange bar on nurse. This orange bar, this orange attention seems like it's the stereotypical antecedent. So there's one head, this orange head, that focuses on the stereotypical antecedent. In contrast, if you look at the green head, that has a large weight on farmer, which is the anti-stereotypical antecedent in the left case. So it seems like these two heads are doing somewhat different things. Now let's switch to the right-hand side. On the right-hand side, we have the nurse examined the farmer for injuries because he. In this case, the orange head now attends to the farmer. Again, associating he with the gender stereotypical antecedent farmer. And the green head now attends to the nurse. So green again looks at the anti-stereotypical candidate. Showing that heads capture different aspects of, in this case, coreference as reflected in our analysis. And in fact, this is consistent with some of the prior work analyzing transformer-based models. So other people found coreference heads, not in the context of gender bias, but just in the context of coreference. Interestingly, in the case of the Clark et al. Paper, they also found a coreference set around layer 5, even though they analyzed BERT, whereas we analyze GPT-2. So two models are different, but they seem to be implementing coreference in a similar way. So this was one example. We've looked at a bunch of qualitative examples that I'm not going to go through in details. What I'd like to highlight, just two aspects. One is that this pattern, in a particular model, the qualitative pattern is consistent. So this is a different example, again showing the same heads, and they fulfill very similar roles. One of them is looking at the anti-stereotypical candidate, one of them is the stereotypical candidate. And we saw that in a bunch of different examples. So within a model, the heads seem to be doing the same things. I don't have the examples here, but I'll just comment that if you look at other models, then we can identify roles, different roles for different heads, but they are not necessarily the same roles as we've seen here. Okay. So this was for attention. Let's look at how neurons work together. So this goes to one of the questions that was asked before. We want to run a similar kind of analysis, comparing the indirect effect from all neurons independently summed up to the indirect effect when you set the mediator to be all neurons at the same time concurrently. The problem, though, as illustrated here, if you look at the right, when you set all the neurons to be the mediator, that actually changes the entire model. And that means that it ends up being equivalent to the total effect. So we can measure it, but it's just kind of redundant. But still, we can look at these numbers. Here I'm showing this comparison of the NIE all and NIE sum. And the main point to note here is that the NIE all is far greater than the NIE sum. Or in other words, when we intervene on neurons independently and then sum them up, we don't get a very large effect. When we intervene on all the neurons together at the same time, we get a very large effect. So we take it to mean that neurons work together in a synergistic way and amplify or compound their independent effects. Okay, so the last question that we have is, how do these all different kinds of effects compare? I've talked a lot about total effect, direct effect, and indirect effect. But how does the total effect actually decompose to direct and indirect effect? And is more of the effect direct or indirect? So here's a look at that. Here we are comparing the direct effect of the entire model. So this is again on attention heads to the indirect effect. So we have a NDE, that's the direct effect, and NIE is the indirect effect. The point to note here is that the NIE all is greater than NDE all, meaning most of the effect is indirect and more indirect than direct. Or in other words, because we are looking at attention heads, most of the effect is mediated via attention heads in these models. That is not to say that the other components are not important. There is still non-negligible amount of a direct effect. And so other components like word representations and neurons and hidden states are responsible for some portion of the effect. Okay. And next, here's a comparison of the total effect to the previous numbers. So in green, we show the total effect, and the orange and purple are again the indirect and direct effect. What we see here is that the total effect is roughly equal to the sum of the indirect and the direct effect. And this was a very surprising result for us. It's actually known that there is equality in linear models. This can be shown. But in a model, highly nonlinear model like GPT-2, we don't necessarily expect this kind of behavior, but we do see this, which is, I think, an interesting observation, which we're still analyzing. Okay, I'm gonna skip this. This is kind of a very similar result on the sum of NIE and NDE, just showing it for specific heads rather than the entire model. So before I go to the work and conclude, I'll stop again for questions if there are any. Okay, so if there are no questions, I'll move on to the future work part. So we have a few ideas on how to extend this work. There are some direct extensions, for instance, studying other models, other architectures, objective functions, and so on. We've only focused on GPT-2, but the same methodology can be applied to various kinds of models. We would also like to study a more inclusive gender notion rather than this binary notion of male and female distinction. We know that there are actually more nuanced views of gender, as well as other kinds of bias, be it racial bias or other biases. Or more generally, we think this methodology can be applied to study various kinds of language properties. That may require us to formulate different kinds of interventions and of course, use or come up with other data sets to study other kinds of aspects of language. We also think these ideas can be used for debiasing. First of all, to assess how good are existing debiasing techniques. and maybe even to help come up with new ways to debias. For instance, one idea would be to use this mediation analysis to specify a location, a component in the model where we want to intervene. So if we find that there is one particular attention head or neuron that causes the bias predictions, that's maybe the place we want to intervene to establish fair predictions. I should also comment that we have actually a very simple case of mediation analysis, or more generally, causal inference. In the real world, we can't really apply those interventions that we have applied and observe different outcomes under different interventions, because you just can't repeat the same intervention, different interventions on the same unit. But if you have a person who is receiving some drug treatment, you either give them aspirin or you give them something else, but you can't do the same, you can't give them both treatments from scratch. But we have complete control. We can run this model as many times as we want. So we have kind of a nice, easy case to observe counterfactual outcomes. And there are other ideas in mediation analysis that may be useful. Some people work on mediation in nonlinear models. There are different ways to decompose the total effect. And there's work on path-specific effects. So in our case, we just looked at one mediator, or maybe a group of mediators, but we haven't really looked at the path of how mediators connect to one another from input to output, which is actually potentially very interesting to study in these deep models. Okay, that's all about this work. I'd like to advertise a couple of events. We are organizing the next Black Box NLP workshop at EMNLP. That's also going to have a shared interpretation mission where we're hoping to bring together people in the community working on similar research questions. That all might happen remotely and virtually. We don't know yet. And we'll have an interpretability tutorial at ACL. That's very likely to happen remotely, although I don't think it's been decided yet. But I'll be happy to see any of you there, either in person or via Zoom. And thank you so much for listening.
Yeah, let's thank our speaker. I'll just unmute everyone. Yeah, and let's clap and thank. Okay, so we have some time for offline questions. Feel free to stick around in the chat room if you have questions. We'll be around till about 1:45, I think. And yeah, let's start with Nader.
Hi, thank you very much for the talk. So I'm really interested with the idea of how to utilize this framework for not just analysis, but for example, you talked about debiasing, but in general, looking at learning models using this causal analysis framework. It seems like it would be very difficult to directly utilize this in learning. One, there's the combinatorial explosion that you were talking about before, but also it seems like some of these interventions might be non-differentiable. So do you have any thoughts of ways that this could be utilized in actively training models?
Yeah, great question. I agree this is going to be a challenge. I think a first step would be to take an existing model and actually change it to debias it. Because it might be that a lot of what you need to do will apply also during training. So imagine, for instance, imagine that you identify that there is one head that is responsible and you can change its behavior in some way based on our approach. This might also happen during training. Perhaps we could identify those heads or other mediators as they arise emerge during training by iteratively testing for them. So you could run every once in a while during the training, runs this sort of analysis that we do to identify these mediators, and if they are above some threshold, you do something to change the behavior of the model. It might be difficult computationally, but I think it is potentially possible. I also kind of like this idea of the path-specific effects, because I imagine, I'm not sure this is true, but I imagine that as we train the models starting from scratch, there may be different paths that arise to mediate these biases. So if we identify a path, we could potentially cut it, kill it, or change it in some way. This is all going to be computationally quite intensive. But on the other hand, training these models is very intensive. So if you every once in a while run this kind of analysis, I think it's not that bad compared to the total training time.
Thank you.
So I had a question about the definition of bias. So if I remember correctly, it was defined as probability of the stereotype divided by probability of anti-stereotype. Was that right?
Yeah, it was the other way around, but it doesn't
Okay.
really matter.
Right.
Let me go back. Yep.
Yeah, I was just wondering whether like what the actual probability values are, and like is it possible that the probability values are quite small and that amplifies the ratio? Or
Yeah, that's a good question. So the probability, the actual values are in the ambiguous cases are not that small.
okay. Mm-hmm.
But they do vary. So there is a large variation between examples, and that's the reason we normalize everything by dividing. Unfortunately, that does lead up to cases where the numbers blow up because occasionally you'll have a very small number that you divide by. One thing we did to mitigate it is we filter out some very, very extreme cases from this analysis, so that helps a bit.
I see. Okay, thank you.
Hi, thanks for the talk. I have a question from the slide 44.
Yeah.
So here, as you can see, that the model is random. It's not trained, but still the most of the impact is coming from the layer 0. And so I'm wondering, why is that the case? Like, is it consistent? And if so, why do you think is it the case that it's focused from one layer?
Yeah, I'm not sure I would read too much into this numbers, so into this plot. So if you look at the scale is very, very small. So even, it's 0.004 or something like that. I'll go back and compare it to the previous numbers that we had. So here you say it's 0.04.
Yeah.
So it's an order of magnitude smaller than the trained model. There might be something there in the fact that the first layer seems stronger, but I'm not sure we can read too much into this.
Yeah, thanks.
Okay, I don't think I see any more questions. I think let's thank the speaker once again, and Yonatan, we'll probably hang around in this room for another 5 minutes before the one-to-one meeting starts. So yeah, let's just thank the speaker once again. Yeah.
Thanks so much. Thank you, everybody.